other half of the immune system. And, oh man, we got a lot of stuff. We got a lot of time. This is the only class I'm ahead in. Every other class I'm behind in.
Oh, next week we're supposed to have snow day.
Oh, you expecting a snow day?
No, yes. Oh, they said like first one.
No.
Yeah,
On
Wednesday.
what night?
Monday night.
Wednesday.
Monday or Wednesday?
Wednesday. It's Wednesday through Friday.
No
Get like a foot.
ways.
Yeah.
God.
Tuesday and Wednesday, 80% chance of snow, but that could change.
My son went home after class today and he called me and he said, so you know our yard light pole? He said, yeah. I thought, oh God, did you run into it or something? He said, yeah, it's knocked over and broken. The wind knocked it over.
Oh.
That's how windy it is. We live up on a hill. So our next test is on the 21st, over only 3 chapters. So that one, everybody should get A's on. A's or B's. So we should be pulling our grades up here.
17, 18, and 20.
Pull our grades up here with the easier test. 17, 18, and 20. Yeah, we're not doing this.
I'm so
And then we've
excited.
got a catch-up day, so, I don't know. Anybody want to start their presentation on the 19th?
We've got to write it first.
Anybody want to volunteer?
I'll do it on the 19th.
If you want, we'll see.
Just don't count on it. Just let it happen. Snow.
That would put us way
I didn't
behind
hear
in
about
foot of
this.
snow.
In Rapid City or the hills.
That would put us way behind in Fizz.
Oh my God.
Because of the Monday?
Oh my God. Yeah, we're already so far behind.
It'd be a whole week behind.
In what class?
In our
What
physiology.
system do we want to skip?
Yeah.
Reproduction.
Yes.
I'm serious, that's what we need. I found out that today. Yeah, that's the least, you know, kind of nursing monitoring system. Nobody goes and says, hey, I'd like to check your uterus because you're here for. Yeah. Seriously, that might be one chapter. Quit talking so much. All right. There's that. Didn't work. It's so fun. All right. So we started last time with the immune system and the non-specific side of the immunity. And I showed you this chart, and I like this chart. And I'm going to draw it out again because I just like it so much. I'm going to put it over here so that we can refer to it when we get to the next chapter. So we've got our non-specific side, and we've got our specific side. Non-specific is otherwise known as innate immunity, and the specific side is acquired immunity or adaptive. It just depends on what book you read. So those are the two sides, and within that, we've got 3 lines of defense, right? Do I need to separate you two? First line of defense second line of defense, third line of defense. First line we said was our physical barriers that keep the organism out, right?
Yep.
We did all this already. This is in your brain. Second line of defense is if they get broken, their first line of defense get broken, then we're going to end up in an inflammatory response. Which is the main part of the second line of defense. We're going to have some inflammation. Which cells are in charge of the second line of defense?
Chitosins or
Who? Neutrophils and
macrophages.
so our phagocytes, right? Our phagocytic cells are the big dogs of the second line of defense. Now we're going to move on to the third line of defense. And the third line of defense has two sides to it. We've got the cell-mediated and the antibody-mediated. And they work hand in hand. You can't really have one without the other in order to have an appropriate immune system. And you need all three. I mean, you need your second line of defense, you need your first line of defense, and you need your third line so we can stay healthy. All right, this is now chapter 17. A couple of terms we have to identify. Number one is an antibody. And an antibody is going to be abbreviated AB. And it is a protein. It's a protein transcribed and translated in certain cells called B cells. B cells make antibodies. Antibody is the term when we talk about them as a group or as a class. You have antibodies, but if we're going to talk about them as individual types, then we say immunoglobulin, and it's abbreviated IG. So we've got 5 different types of antibodies, 5 different classes of antibodies, and when we talk about them individually and what they do individually, we use the term immunoglobulin. We don't say antibody A or antibody B, we say immunoglobulin A or B. All antibodies have a similar structure. They're Y-shaped protein, and the leg portion, the foot portion, and the leg portion, and the arm portion is constant. That's the same in all antibodies. It's the hand portion that changes. So it's the hand portion of the antibody that's going to bind to different antigens. Bacteria, E. coli, Staph epi, Staph aureus, COVID, influenza, hepatitis, whatever. The hand portion is what changes. And each antibody can make, each B cell can make a different type of antibody. We can make antibodies to detect really anything that we come across. We should be able to fight any infection we come across, right? I'm probably never going to get infected with malaria. I mean, I don't know. I'm not planning to go to tropical areas anytime soon. I suppose I could. Maybe I'll get infected with malaria.
If you're
Not
lucky.
anytime, right, but if I'm lucky. If I'm lucky. But could I fight it? Would I build an immune response against it? Sure, I have the capability. I just haven't seen it yet. So it's the hand portion that changes. And so you've got, these different structures that can do, oh my gosh, look at all these we can do. Oh, I did that one. We can do, this one. How about this one? How about that one? How about, there's that, and this, and this, and this. See? Look at all the way I can do. This, and this, and this, and this. We can do anything. We can make antibodies with different hand portions that can bind whatever. They can bind to whatever. And within the classes, the different 5 classes, they all do a little bit different job. They all have a little bit of a different function. And I show the image here as a table. So IgGs make up 80% of your antibodies. the vast majority of your antibodies are IgGs. And they hang out as what's called a monomer, just a single antibody like this that can float through the bloodstream. IgGs can cross the placenta. They're found through the bloodstream. They're found in the intestines. And they are the longest living. They have a half-life of about 23 days, so they get secreted. In 23 days, half of them die. In another 23, half of those die. And another 23, half of those die or get destroyed. The main job of the IgGs is to surround bacteria or viruses. They surround the antigen. And we'll talk about that here in a second. IgM is the next most abundant. 5 to 10% of your antibodies are of the IgM type, and they're kind of held together in sort of a snowflake appearance. I think they're kind of pretty. Snowflake appearance. IgMs are too big to cross the placenta. They're too big. So if you remember your blood types, right? Old physiology people, we just did this. If you're A blood, right? You've got A proteins on your red blood cells, and you've got antibodies that recognize B blood naturally occurring in your blood, right? Okay. If mom is A blood and dad is B blood and baby is B blood, how can I have a mom that's A blood and a baby that's B blood, and these antibodies don't cross the placenta and kill the baby? Because they're IgMs. They're too big. These guys are the snowflake. They can't cross the placenta. So babies can be a different blood type than moms, which happens all the time. Okay? Happens all the time. A little shorter half-life. These guys are also, their job is to surround antigens, surround foreign things, and target them for destruction. They tend to be the first antibodies produced in a response. They're the first produced, the first type of antibody produced, and then the second type will be IgGs. IgAs hang out with their little feet stuck together in a little, what's called a dimer. I'm sorry, these are the second most abundant. This is the third most abundant. IgAs are the second most abundant. 10 to 15% of your antibodies are of the IgA type. They are found in breast milk. This is the immunity you give baby when you breastfeed. So when baby breastfeeds, they literally eat the antibody, and somehow it doesn't get destroyed in the stomach acid. I don't know how, but it doesn't. It should. It's just a protein. It should be denatured like anything else. But it provides the baby some immunity because of their antibodies that bind to stuff that baby's never seen before. And, but they only last about 2 to 3 weeks. So once you quit breastfeeding, then those will start to die off.
I was gonna ask if like formula has that?
No.
So is it kind of
It
a
comes from,
downside then?
yes.
Okay. Now, has there ever been like related deaths due to pregnancy and the placenta not blocking out blood? Is the antibodies?
Not that I know. There's a different type of reaction that occurs across the placenta.
Is that the colostrum or the?
The colostrum is just the early milk is high in those antibodies.
Ah.
It is high in those antibodies. It's got really concentrated, thick early milk. But still breast milk has it. You have these antibodies in your mucous membranes, you have them in your intestines, you have them in your saliva, your tears. They act as kind of part of the first line of defense. So they'll bind up pathogens so that they can't attack you. IgDs are quite rare. They're a monomer. They're a single type antibody. And they believe their main function is not known in the blood, but they do stand on the surface of a B cell. and act as a receptor. So their little hand portion will be specific for something, and so they act as a receptor for B cells. And then IgEs are the most rare. These also stand on the surface of some of our cells, a cell called a mast cell. And another cell called a basophil. We talked about basophils. So these IgEs stand on the surface of these guys, and they bind to things that are allergens. So when the allergen, if you're allergic to pollen, you develop these antibodies after you're exposed to it. They stand on the surface of these cells. The next time you get exposed to the pollen, it binds to the receptor, or the hand portion, of the IgE, and that causes the mast cell and the basophil, because it works the same way, to release histamine. And histamine is what causes those allergic reactions. Leaky blood vessels, fluid buildup, edema, swelling, itchiness, constriction of bronchioles and muscles in the throat and stuff like that. And antigen is going to be abbreviated AG. This is anything that initiates an immune response. Anything that initiates an immune response. On the surface of our antigens, we have structures, whether they're small proteins or carbohydrates or whatever that are on the surface that the antibody binds to. These are known as epitopes. So the epitope is on the antigen, and it's what the hand portion is specific for. So notice this antigen has multiple different epitopes, which means that many different antibodies can bind to those different surface structures, and then what that does is it targets the cell for destruction by the immune system.
So the epitope is a receptor on the.
Epitope isn't a receptor, it's usually either a protein or a carbohydrate, something on the surface that the antibody is recognizing. It's not a receptor though.
Do they have to be attached to the same shape?
Yes. Each antibody will bind to its own epitope. It's acting as a target.
It's an attachment site.
It's acting as an attachment site. A receptor is, it's just different. It allows for the binding of something to cause an action inside. This isn't causing an action. This is just something that it's going to stick to, that the antibody is going to bind to.
Like a glue. Right?
All right, so we've got some different types of immunity to define here. If it's naturally acquired active immunity, naturally acquired means you catch it, basically. You naturally acquire it. If it's active immunity, that means your immune system is activated by whatever you naturally came across. You get COVID, you caught COVID naturally, you build antibodies, you had an immune response, that's naturally acquired active immunity. If it's naturally acquired passive immunity, you get the immunity through a natural type process, but you are not the one making the antibodies or having the immune response. This is the example of breast milk. So babies breastfeed, that's a natural process. They're getting the antibodies in the breast milk. The antibodies are providing some assistance to the baby, but the baby didn't make them, right? Baby didn't make them, so it's passive immunity. Naturally acquired passive. Artificially acquired active immunity is where you're going to make your own immune response, but you didn't naturally get the infection. So this is a vaccination. You got an injection with a piece of COVID or a piece of a bacterium or whatever, and then you build an immune reaction against it on your own. You do it yourself. And then the last one is artificially acquired passive immunity. Again, passive means you're not making your own immune response, you're getting it from somewhere else. And if it's artificially acquired, it's usually done through an injection. These are IgG shots, or not IgG shots, but gamma globulin shots. So if you take proteins in the bloodstream and you separate them out on, you can separate them out by size on what's called a gel by electricity, and they will separate into these fractions. And this one is albumin, which is one of our plasma proteins, and there's the alpha, beta, gamma fraction of our globulins. This gamma fraction is full of antibodies. All the antibodies are about the same size. And so you collect them out of this fraction, and you purify them, and you put them in a shot, and you inject them into people, like military people, who are gonna go TDY or go PCS or wherever overseas, and that gives them a boost of immunity that they didn't make on their own. So, artificially acquired typically involves an injection. Active means you make an immune response on your own. Passive means you're getting the immunity from somewhere else.
So do you know why patients need more vaccinations after they have like a spleen?
More vaccinations after a splenectomy.
Yeah, like
Well, a
after-
spleen is part of the is part of the lymph system, which has got tons and tons of white blood cells in it.
'cause,
So
like,
they're
after-
probably, if you have a splenectomy, you're probably gonna be slightly immunocompromised. I'm guessing.
I just know that like after my patients with like holidays and medicine, like they have a series of vaccinations.
Say that again.
After we like after one of our patients has a splenectomy, they come in and we give them like a huge series of vaccinations over the course of like 2 years.
I don't know, I don't know.
I don't know if that has something to do with it.
I mean, like I said, the spleen is part of the lymph system, which has got tons and tons of white blood cells in it. It also destroys old red blood cells, but that doesn't have anything to do with it. I don't know why. Well, maybe it's full of lymphocytes, which is where your immune cells that remember infections live. They like to live in your lymph system, so maybe that's why. Humoral immunity is antibody-mediated immunity. This is run by B cells. Cell-mediated immunity is run by T cells. So if we head back over here, this is our third line of defense. Antibody-mediated, who makes antibodies?
Immune system.
Which cells make antibodies? B cells. Okay? So if B cells make the antibodies and run the antibody-mediated side, T cells run the cell-mediated side. We know what cytokines are, right?
Yes.
Cytokines are a chemical released by lots of different types of cells. There are tons of different immune cytokines. Immune cells like to talk to each other through these chemicals. And there's just tons of them. I can't even list how many there are. There's a bunch of them. We know that apoptosis is programmed cell death, and necrosis is death by damage. So all of our cells have a programmed lifespan. They live a certain length of time, and then they're told to pull away from their neighbors and implode. And usually, but not always, they're replaced. Like your digestive tract, the lining of your digestive tract is replaced about every 3 to 5 days. So every 3 to 5 days, we're going to start undergoing apoptosis, and they'll be replaced. Other cells don't have multiple sort of lifespans within your lifespan. They live your whole life. Like a lot of neurons live your whole life. Muscle cells, cardiac muscle cells, their programmed lifespan is the length of you. If you have a heart attack and you lose blood flow to your heart, then you're going to have necrosis, which is death by damage, loss of oxygen, the cells are starving, they can't make ATP, and then they explode, which then causes collateral damage and inflammatory response. Inflammation. Okay. B cell side. We're going to talk about the antibody mediated side first. B cell side first. B cells are produced in the bone marrow, just like all of our blood cells. All of our blood cells are made in the bone marrow, and then they leave the bone marrow as they mature and head through the bloodstream and sometimes to some different tissues. B cells like to go to the lymph tissue. B cell is a lymphocyte. Got that big round nucleus. They live in the lymph tissue, which includes your lymph nodes, your spleen, your Peyer's patches of the gut, and that's where they hang out. Each B cell can or has the ability to make any type of antibody. And when the B cell is going to make an antibody, that is the antibody it makes. But we have enough B cells that we can make antibodies to pretty much anything that we come across. So if in our bone marrow, we make these 4 different B cells, and this B cell is the one that binds to the antigen, then what's going to happen is it's going to divide and divide and divide many times, and ultimately turn into a cell called a plasma cell. A plasma cell is the cell that is actually the antibody producer. Each of these plasma cells can spew out antibodies to the tune of about 2,000 per second. And each of these plasma cells is going to make the same antibody that recognizes the antigen, and we're just going to spew out millions of antibodies, which are going to go bind up the antigen and block it from infecting you and target it for destruction. One of the caveats here is that the B cell cannot become a plasma cell without some instructions from the T cell side. So we've got our B cells, we know which antibody we want to make, we want to turn into plasma cells, we want to spew out all these antibodies, but we can't do it because we need permission from our T cell side. The other thing that B cell is going to do is, besides do the antibody production factory, it's going to make a B memory cell, which remembers that we've seen this antigen before. So if you get it again in the future, you've got these memory cells that can start to attack it right away. That's part of our immunity. Some immunity lasts a long time, some immunity doesn't last a long time. It kind of depends on the level of the disease with both memory cells. We're going to have T memory cells and B memory cells. And it kind of depends on the level of the disease. Like, if you had a really bad case of chickenpox as a kid, before they had the vaccine for chickenpox, you'll probably be immune from chickenpox for life. If you had a weak case of chickenpox, you might not have lifelong immunity. It just depends. So, how do antibodies work? People like to think that antibodies are little grenades that get released and then blow things up, and that's how antibodies work. Well, they don't. Antibodies don't kill at all. They really don't even damage anything. What they do is multiple things. One of the things they do is surround an antigen. They bind to the epitopes on the foreign thing. And by surrounding, it's called opsonize or opsonization. And if you've got an opsonized bacterium here that's surrounded by antibodies, then macrophages and neutrophils find it and eat it faster. So the example I always like to give is, brownies are good, right? We eat brownies, yummy. Macrophages would probably eat brownies, but frosted brownies, those are even better. If I'm gonna choose between a brownie, frosted and unfrosted, going for the frosting. So we can think about these antibodies, this opsonization, like frosting for the antigen. Covers it, makes it yummier. The macrophages and neutrophils see it faster. They could eat the bacterium on their own, but it's not nearly as good as if you put frosting on it. Then they go after it even faster. So, did the antibody kill the organism?
No.
Nope. It targeted it for destruction by your phagocytes. Second way that antibodies help with killing organisms is through that complement system. Remember, complement was part of our second line of defense, and it was those 9 proteins that float about in the bloodstream, and they form holes in the bacterium, which causes the insides to fall out in lysis. Well, the way that complement is activated is if you've got antibodies covering the organism, complement comes and cross-links to antibodies, and that activates the complement. This then calls on its other 8 neighbors, and they stick themselves into the cell and cause lysis. Again, the antibody didn't do anything. It was just there to activate the complement. Third thing, opsonization, besides making frosting and making the macrophages and the phagocytes eat it faster, is that opsonization then blocks the organism from sticking to your tissues. What does a virus have to do to infect your cell?
Enter. Bind.
Bind to receptors. If this virus is surrounded by frosting, can it bind to the receptor? Nope. And it ain't going to infect the cell. So we're not going to make 200, 300 more viruses. Same thing with bacteria. Remember, bacteria have to adhere to your surface cells, or your surface receptors, before they can start to divide, right? They have to stick. If they can't stick, they can't divide, and so they're left worthless. So this is called neutralization. So they're neutralized. Do you remember when they were talking about COVID, and that was so long ago. One of the things they talked about was neutralizing antibodies. Did you ever hear that term? The neutralizing antibodies were the antibodies that you were produced either after natural infection or after vaccination. They're the guys that are out there opsonizing COVID and not allowing it to bind to your cells. That's what they were measuring, the neutralizing antibodies. And no matter when you get an infection, you make tons of neutralizing antibodies. But naturally, they rise and then they fall. So if you get over the illness, you don't need all those bunches of antibodies around. So they're going to drop. They're going to drop to some level. That's what they were talking about. So that was all fine and well and good. Oh, well, we don't have as many neutralizing antibodies as we did before. Okay. But you still have these potential memory cells that can make more of them if you see it again. So this is all, learning. We're still learning about this. This is, you don't learn everything about a brand new disease and how the immune system's going to work and how long the immunity lasts in 2 years. We don't know. We just don't know yet. Toxins from bacteria, like AB toxins, superantigens, those kind of things, they can be neutralized by antibodies as well. And then they can't bind and enter and disrupt protein synthesis. Fourth way that antibodies work in the immune system is by something called agglutination. Oh gosh, we just talked about this in lab. Agglutination is where you've got antibodies that bind to, in this case, bacteria. And then what they do is they stick to their neighbor, like so. and they form these big clumps called agglutination. These clumps make it, again, easier for your phagocytes to come along and chew it up. It assists phagocytosis. This is the clumping. This is the big pile of antibody, bacteria, virus, antigen clump. And the last thing that antibodies do is something called antibody-dependent cell-mediated cytotoxicity. What the hell does that mean? Antibody-dependent, meaning antibodies are required. Cell-mediated, we're going to use some other cells. Cytotoxicity, we're going to create some poisons to damage some cells. Here's how it works. This system is used for looking at large or dealing with large parasites, typically worms. Something that's bigger. You can't phagocytize a worm, right? A macrophage can't eat a whole worm. So how are we going to get rid of it? Well, this is one way. Antibodies can bind to it, but they can surround it all day long with frosting, but the macrophage can't eat it, right? You can't eat a whole worm. Worms just kind of live there. They don't really bind to receptors, so you can still put the frosting on it and it doesn't neutralize it at all. It just has frosting on it, so whoop-de-doo. But eosinophils, which is the white blood cell with the big red granules, they can come along, bind to an antibody that's frosting our worm, and by binding to the antibody, it causes the granules in the eosinophil to be released. These are poisonous chemicals, and they blow open the cell membrane, which we hope can then kill the worm that way. Interesting.
Could this happen again? Like any foreign body in your body?
No.
No.
No. Because this foreign body has to have a cell membrane to cause lysis. The other side of the cell of the third line of defense is our T cell side, or our cell-mediated side. So we've got our B cells that make antibodies. B cells that make antibodies. They're going to turn into a cell called a plasma cell that we'll come back to. Plasma cells are going to make antibodies. Do antibodies kill anything?
No.
No. T cell side is the side that's going to do our killing. T cell side are killer cells. T cells are made in the bone marrow, just like all blood cells. Then they travel during fetal development to an organ that sits above your heart called the thymus. It sits about right here. And in the thymus, the T cells read the book of you. They go to school. They go to U school, U University, and they learn everything about you. In other words, on all of your nucleated cells, we have a specific protein complex called MHC. And MHC is what identifies you as you. We've got two kinds of MHC, MHC1 and MHC2, and they're used in different sort of mechanisms, but they identify your cells as you. And it's a complex 4-gene system of proteins that you inherit from your parents that identifies you as you. So you share half of your MHC with your mom and half of it with your dad, and it makes you unique. So if my cells have an MHC that looks like that, that identifies that cell as Pam. And my T cells learned that that belongs to me, and they better leave those cells alone because we don't want to hurt those cells. They belong to me and the body that I live in. Now, if I were to be given an organ, like a new liver, unless I have an identical twin, which I don't. Anybody got one in here? Okay, we're all out of luck. We don't have identical twins. So, any organ that I'm gonna get is gonna have a different MHC on it, right? These are complex. The odds of finding your exact match is like nothing. So, in the olden days, they used to do tissue typing and they tried to match the MHCs to make them as close as possible. Was it a good tissue type? Was it a good match? Now it's basically blood type. If it's the same blood type, you can get an organ from whatever.
What's known as olden days?
Probably 20 years ago.
Okay.
Nowadays, in the new days, in the modern days, the drugs we have to suppress the immune system are amazing. So you don't even have to worry about the MHC. So let's say I needed a new liver and the MHC is like that. Well, my T cells, which are gonna be, they're the ones that kill. They're gonna run around there and say, oh, that doesn't belong, and I'm gonna target that for destruction. And then I have rejection, organ rejection. So what the drugs that we have now, these amazing suppressive drugs, basically put dark glasses on your T cells so they can't see as good. And they go by and they're like, yeah, that cell's alright. That's good too. Okay. We're all good. Everything's fine here. It's all good. And they can't see. And that's the way immunosuppressive drugs work. So if you're on immunosuppressive drugs, that's great for your liver that you just got from somebody else, but what does it do for COVID?
Immunization for
That's it.
infection.
It make your immune system is, oh yeah, COVID's fine, dude. Yeah, come on in. Join the party, right? They can't see it. So people that were immunosuppressed, transplant patients, usually got much sicker with COVID because their immune system is dampened down.
So in autoimmune diseases, does it just stop like recognizing your MHC1s as yours?
No, in autoimmune diseases, usually autoimmune diseases follow some kind of a virus. And so you get a virus. Okay, we get a virus from spikes, right? Your immune system sees it. We make antibodies that are gonna opsonize the virus and target it for destruction. We get rid of the virus. Everything's fine, right? Weeks, months, years later, these antibodies that are still hanging out in your immune system or in your blood system start to look at your cells and say, oh, wait a minute. There's a structure on that cell that reminds me of that virus, and I'm just gonna target that for destruction. That's one way autoimmune diseases work. Yes. Sometimes they bind, or the cells will target tissues, release cytokines that result in mass, like inflammation.